Hello, my name is Param Hanji, and I will be presenting noise-aware merging of high dynamic range image stacks without camera calibration. In HDR imaging, the conventional way of capturing all the information present in a natural scene is with a stack of images taken with different exposure times. These are later combined and processed to produce a visually pleasing HDR image, preserving details in bright as well as dark regions of the scene. The probabilistic photon registration and electronic processing in modern cameras result in some variation in the values recorded in each pixel. This manifests as noise in images and is particularly problematic for low exposure images. Any method attempting to accurately estimate the underlying scene radiance from multiple images strives to increase the dynamic range while simultaneously reducing such noise. To understand the sources of noise, we summarize the image formation pipeline in modern cameras. Photons from a scene are captured by the camera lens and pass through a color filter array before being focused on an imaging sensor. When exposed for a fixed interval, the sensor converts some incident photons to electrons. These electrons accumulate to yield a voltage, which is processed by analog electronics. An important operation here is the amplification of the signal by a gain based on the specified ISO. Next, an analog to digital converter digitizes the signal into discrete pixel intensities. Finally, the image is transformed by operations of the digital pipeline before being saved on the file. As alluded to earlier, digital values are inaccurate measurements of the scene radiance due to various reasons. The process of photon registration by the sensor inherently follows a Poisson distribution leading to the first source of noise called photon noise. The variance of photon noise depends on both the scene radiance and the exposure time, making it signal dependent. Other sources of noise approximately follow a zero mean normal distribution and are signal independent or static. Readout noise captures fluctuations in the voltage while accumulating electrons and is amplified along with the signal. The last component, analog to digital or ADC noise, is added after amplification and is attributed to the quantization error. Noise calibration refers to the estimation of the five camera specific parameters: standard deviation of readout noise, standard deviation of ADC noise, and three color coefficients to account for the different photon to electron conversions for red, green, and blue channels. Rather than measuring the noise added from various sources individually, we used a calibration target constructed by overlaying a uniform light source with neutral density filters of different transmittance values. The images provide measurements of sensor noise at different signal intensities to fit the noise model. Please refer to the paper for further details. Here, we show the measured data points as crosses and model predictions as lines for the green channel of our calibrated cameras using multiple ISO values. The statistical noise model explains the variance of pixels observed in real images of several different types of camera sensors, from a small smartphone sensor to a full frame mirrorless sensor. For a single pixel, given a stack of noisy measurements xi, where I is the exposure index, we want to find the most accurate estimate of the underlying radiance phi. Early HDR heuristic estimators were not motivated by a statistical noise model. The popular hat-shaped estimator proposed by Debevec and Malik, for instance, assigned higher weights to pixels whose tone map values were close to mid-gray levels. With a calibrated noise model, better estimators were derived by approximating the Poisson component with a normal distribution and then maximizing the log likelihood. The analytical variance weighted estimator was obtained by assuming that the per pixel scaled measurement x and variance sigma squared are independent. Alternatively, the iterative expectation maximization or EM algorithm leads to a more accurate estimation of the radiance. However, both these estimators are highly sensitive to the calibrated noise parameters, which are difficult to obtain in practice. Instead, we show that a comparable HDR estimation is possible by ignoring the contribution of static noise and then maximizing the log likelihood. The Poisson photon noise estimator, or PPNE, has a simple analytical form enabling the efficient computation of the radiance. An added advantage is that knowledge of the noise parameters is not required to provide accurate estimates. We rely on Monte Carlo methods to quantitatively evaluate the HDR radiance estimators on a synthetic logarithmically spaced gradient spanning 24 stops of dynamic range. We use 10,000 HDR stacks, each consisting of 3 images with a separation of 5 stops and a constant gain of 8. This tone map figure depicts the ground truth gradient as well as synthetically generated images with different exposure times. The noise in our simulations was generated according to a well-validated noise model and using parameters obtained from calibrated cameras. Thus, it closely resembles the camera noise seen in real images. The empirical biases and variances of the estimators are compared for the Sony IMX345, a smartphone sensor, as well as a high-quality imaging sensor present in a full-frame mirrorless DSLR. We show relative quantities because they better correspond with perceived magnitudes according to Weber's law. The hat-shaped estimator that does not account for noise results in the highest bias and the highest variance. The popular variance-weighted estimator performs reasonably well for the high-quality sensor, which results in a noisy estimate with a negative bias for the mobile phone sensor. Overall, the error of PPNE is comparable with that of the EM estimator, which is the best estimator used in practical applications. Further, we prove that PPNE is unbiased and has the minimum variance among all the estimators for the simplified noise model without static noise. This is an important result, since estimators produced by maximum likelihood estimation are generally not guaranteed to be unbiased or to have the minimum variance. The sawtooth patterns visible in the standard deviation plots are due to the 3 exposures. The highest 5 stops are captured only in images with the shortest exposure time, and therefore the error drops when data from the second and the third images become available. Next, we show visual differences in HDR images due to the choice of the estimator by comparing them with the accurate EM estimator in challenging conditions. We captured 3 images of the depicted scene with a calibrated camera. The shortest exposure image was deliberately underexposed to highlight the differences of the estimators in noisy regions. The results are consistent with the quantitative analysis presented earlier. The hat-shaped estimator produces a large positive bias and noticeable salt and pepper noise. As predicted by the simulation, a slight negative bias is visible for the variance-weighted estimator. The image generated by PPNE is surprisingly robust to the high noise present in low luminance regions, and it is almost indistinguishable from that produced by the more complex iterative EM estimator. A significant advantage of PPNE over the EM estimator is that it does not require knowledge of the noise parameters. Therefore, it can be used with any camera without prior calibration as long as the camera's noise characteristic is well explained by our model. Finally, additional experiments detailed in the paper indicate that the relative performance of PPNE does not degrade under different capture strategies and under increased noise, making it an attractive estimator for HDR imaging. Thank you for watching. For more details, be sure to check out our paper and the supplementary material.